All right, let's get started. So today we're going to have our second lecture on model-based reinforcement learning, advanced model-based reinforcement learning. Before that, just one announcement. Homework 3 is actually extended by a week. It'll be due the week after next, and there was a post by Kate on Piazza about this, so you do have one more week. It's because we had to shift around our schedule a little bit since we're still in the process of finalizing the next couple of homeworks. So once we figured out what the next homeworks would completely contain, we decided we can give you guys one more week for this one because we know that some of the training times for homework 3 can be quite long. But nonetheless, do make sure that you start on homework 3 early because, you know, I think there were already some posts on Piazza about someone saying that on their laptop they were expecting this thing to take multiple days to train. Okay, maybe that was a particularly slow laptop. My expectation is actually on CPU, it should be about 12 hours to train and 2 to 3 hours on GPU. But if you have an older computer, it might take a bit longer than that, so do be careful. All right, today's lecture. So today we're going to talk about two main topics. The first one is going to be managing overfitting in model-based RL. So I'm going to talk about what the problem there actually is, how do we represent uncertainty to try to mitigate that problem, and we'll have a little bit of a brief discussion of Bayesian neural networks and ensembles. And then in the second half of today's lecture, I'm going to change gears, and I'm going to talk about model-based reinforcement learning with images and other kind of high-dimensional inputs. And here we're going to actually revisit the partially observed Markov decision process model. So the POMDP is something we introduced in the very beginning of the class, forgot about for a while we were talking about model-free RL. We'll actually come back to that, and we'll discuss how that actually plays an important role in model-based reinforcement learning. We'll talk about learning encodings of observations to acquire latent state representations, learning dynamics-aware encodings, and then we'll kind of survey some recent papers in the literature that talk about this. So the second half of today's lecture will really be kind of a whirlwind overview of recent papers because this is a very open research area and there isn't a single concrete answer to the best way of doing things. So the goals for today's lecture will be to understand the issue with overfitting and uncertainty in model-based RL, understand how the POMDP model fits with model-based RL, which will be in the second half of the lecture, and understand recent research on model-based reinforcement learning with complex observations like images. And actually, some of the recent research that I'll talk about in the second half of today's lecture might also give you guys some ideas about things you might want to do for your final project, perhaps. Okay, so but let's start with number one. Let's start with managing the overfitting problem in model-based RL. So this is a plot from a research paper, actually from 2018. And what this plot is showing is, it's meant to show some comparison between model-based and model-free learning. So let me just explain what's going on in this plot. This little brown bit over here in the beginning, this is what happens when you run model-based reinforcement learning. And then this red curve afterwards, this is just starting from the place where the model-based reinforcement learning left off, and then running model-free learning, in this case, with a trust region policy gradient algorithm. So this is the half-cheetah task. Some of you might have looked at this task in homework 1. Well, hopefully all of you did, but some of you might have actually visualized it and seen what it looks like. It's this little, as the name implies, it's about half a cheetah, roughly. It's a little two-legged thingy that runs in a plane. It's not a very difficult task, but if you want to use a trust region policy gradient for it, you'll take quite a few time steps to get to a good solution, but eventually it gets to a very good solution, to above this 5,000 reward. So concretely, the model-based algorithm here takes about 10 minutes of real time, and after this it actually plateaus, so it doesn't get any better than this. The way this model-based algorithm works is actually very simple. This is essentially the version 1.5 from last time. So here we train a neural network dynamics model to predict ST+1 from ST, AT, and then use the random shooting to choose actions with a horizon of 10 steps. So it's a very simple model-based RL algorithm. It's sort of the canonical version of version 1.5. And that takes the equivalent of 10 minutes of real time. It's not actually 10 minutes in terms of wall clock time. It's if the cheetah was actually running in the real world at real world speeds, it would be running for 10 minutes. The model-free phase then takes the equivalent of about 10 days. Notice that the x-axis is a log plot. So it's a much longer training period, but gets to a much better performance level. And as a practical side note, whenever you guys are working on reinforcement learning algorithms, it's often a good idea not to get too fixated on looking at plots like this. It's a good idea to also actually look at what the heck the thing is actually doing. So we'll do that now. If we actually look at what it's doing after 10 minutes, this is the, let's see if I can play the video. 1 second. I think I have to, 1 second, I just have to restart this thing. Okay. So if we look at what it's doing, there it goes. So this is half cheetah with a reward of about 500. So this is what model-based RL came up with. It's not a bad solution. The cheetah is actually ambling along, just not at a very fast gait. And then after model-free RL, this is what you get. So you get a cheetah that runs really, really fast, so fast, in fact, that it outruns the camera, basically. It's going off the screen. So something is clearly working in the model-based RL case, but it's not working quite as well. So why is that? And actually, if you will implement this method for homework 4, and you will see that indeed it does something, but not something as impressive as model-free RL. Well, the performance gap is due to the following fact, that when you're over here in the beginning of learning, it's very important not to overfit, because if the point of model-based RL is to learn efficiently from smaller amounts of data in 10 minutes rather than in 10 days, you have to actually learn from small amounts of data. And when you're learning from small amounts of data and training a high-capacity model like a deep neural network, overfitting becomes a big issue. So you have to choose a smaller model or regularize that model so that you don't overfit really badly over here. But if you set up your model so that it doesn't overfit, then you might get the opposite problem, that once you're in the high data regime on the right side of the plot, then you might underfit. So the ideal model is something that avoids overfitting in the beginning and has high capacity so that it can represent the true dynamics over here. And it's very difficult to set up models like that. So in reality, you'd probably choose a model that's smaller than what you would usually use or more heavily regularized, in which case you would do well here in the beginning, but then not really succeed. You would plateau and not really get better afterwards. If you choose a model that's too big, the problem is not that you have to wait for long. The problem is that your performance will tank right in the beginning when your model overfits catastrophically and probably never recover. So given the two choices, better use a smaller model, because then at least you'll get somewhere, whereas if you use a big model, it'll just tank right away and never come back. That's a little unsatisfying. We would like to do better than that. So maybe if we want to kind of get the best of both worlds, perhaps first it would be helpful for us to try to understand how exactly this overfitting problem manifests itself. And it manifests itself basically because of step 3. So let's say that you learned a model using some data. So this is, by the way, the version 1.5 algorithm. So this is where you minimize your error, use your model to choose actions, and then you replan using MPC. That's exactly the algorithm that was used on the previous slide. So let's say you learn a model, and what I'm plotting here is a cartoon illustration where the trajectory is on the x-axis. Pretend that your trajectories can be one-dimensional. And the vertical axis is showing the predicted reward of that trajectory. So of course, the way that you get the reward is you actually predict the states and then evaluate the reward of those states. So you can create a plot like this. I don't know, maybe PCA the thing down to one dimension or something. And if you're getting overfitting, what does that mean? Well, overfitting means that the actual trend is something simple. The data is a noisy realization of that trend, and the thing that you fit is way too complicated. And in particular, when you overfit, you make mistakes, and some of those mistakes are optimistic mistakes, meaning you think that a particular sequence of actions is better than it should be, and some are pessimistic mistakes, meaning that you think that a particular sequence of actions is worse than it should be. And it's the optimistic mistakes that really get you, because if what you're going to do is choose the actions with the highest reward, which one are you going to choose? Well, you're going to be really tempted to go for this erroneous peak over here. This picture is a little imperfect because there's actually a taller peak, but if that erroneous peak was the tallest, you would go there, and that's actually not a good trajectory. It's just that your model is so heavily overfitted that it has an erroneous mountain that it built up in the middle of nowhere where there shouldn't be one. So step 3 essentially adversarially exploits the mistakes that the model makes, the positive mistakes, the mistakes where the model is optimistic. And that's really bad news. So what we're going to talk about in the first half of today's lecture is actually how we can mitigate this problem. And to get some ideas for how to mitigate this problem, we'll actually look back at an example from the literature that we saw on Wednesday. So some of you probably remember this video of the robot arm stacking blocks. This is a paper from 2011 that looked at model-based reinforcement learning with Gaussian process models. So just to remind you how this method worked, it was basically the version 2.0 RL algorithm, where you run your base policy, collect data, use that data to fit a model, and the model in this case was a Gaussian process. There's nothing particularly special about Gaussian processes except that they give you uncertainty estimates. So Gaussian processes are Bayesian models, which means that they will tell you not only what is the expected next state, but also what is your uncertainty about the expected next state in the form of a Gaussian distribution. Then, since this is version 2.0, this method backpropagates through the model back into the policy, and then runs the policy, appends data, and so on. And concretely, the way that this step 3 was implemented in this paper, which is not the only way to implement it, but one reasonable way, is that you have to actually account for the uncertainty. So they had this kind of neat method that iteratively projected distributions onto Gaussians. So to remind you guys, basically if you assume that your current state distribution P of ST is a Gaussian distribution, a normal distribution, and P of S prime given S comma A is given by a Gaussian process, then unfortunately P of ST plus 1 is not Gaussian, but it does have a closed form expression that you can write down. So what these guys did is they said, well, let's write down that closed form expression. It's some complicated mess of linear algebra, but what you can then do is you can approximate it with a Gaussian, meaning you can match its moments, to get an approximation to P of ST plus 1 that has the same mean and variance as your prediction P bar of ST plus 1. So that's moment matching. And then they just did this over and over again. So if you take your Gaussian process, you predict your distribution over P of ST plus 1, you get this green thingy, which is not Gaussian, it's some complicated peaky thing. But then if you match its moments with a blue curve, you get a Gaussian. It's not exactly correct, but it's close enough. And then this whole thing is actually differentiable, so then you write down the expectation of the reward under the state marginals and just backprop using your favorite differentiation technique, basically using chain rule. So why am I telling you this? Well, the reason that I wanted to explain this is that the thing that makes this method a little different from most of the methods that we actually discussed last time is that it's actually trying to model the uncertainty in the model. So because the Gaussian process is a Bayesian model, when it makes these predictions about P bar ST plus 1 from P of ST, the variance in P bar of ST plus 1 depends on two things. It depends on the Gaussian process's estimate of the noise in the system, meaning that the transitions are stochastic, and also on its estimate of the uncertainty about the model itself, which the Gaussian process estimates very well. So this is a picture of a Gaussian process, and you can see that, okay, here, this is a cartoon drawing, but you'd imagine you have data points here, 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 and here, and far away from the data points, the uncertainty balloons. So the shaded region is indicating one standard deviation. So it doesn't have to be a Gaussian process, but if it's something that models the uncertainty about the model in a way that the uncertainty increases far away from the data, then you will get higher variance P of ST plus 1s if you're taking actions that take you far away from the actions that you've executed in your data. That's taking you to unknown regions. So why is this a good idea? Why might this mitigate the problem that we saw before? Or put another way, why were GPs so popular in model-based RL? So as I mentioned, GPs give decent uncertainty estimates. There are other models that give decent uncertainty estimates too. And what that means is that when you get far away from the data, the estimated uncertainty increases. That's kind of what we expect. If we're far from anything that we've seen, we're much more uncertain about what's going to happen. So what happens when you actually use this to make decisions in model-based RL? Well, let me illustrate a little example. Let's say that my goal is to walk to the edge of this cliff to get a good view of the ocean. So obviously, if I want to get a good view of the ocean, what I should do is I should approach the cliffside as closely as possible, but not actually go over the cliff, because if I fall in the ocean, then I'm not going to have a very good view. So I have to be very careful. I have to stand right there on the edge to look out onto the water, but not go too far so that I don't fall in the water. And now, let's say that I have low uncertainty about my model in proximity to that state. So maybe this circle represents the standard deviation of my forward predictions in that region. So if I'm standing over here and I move forward, I might be anywhere in this circle. maybe now I'll say, well, going to the cliffside, it's pretty good. Like, almost certainly I'll end up staying on the cliff and getting a nice view of the water. But if my uncertainty is larger, if my uncertainty is like this, then I might choose not to approach the cliff edge, because while I might get a good view, I also have a pretty good chance of simply falling off the cliff and getting a very, very negative reward. So if I figure out what is my reward in expectation for a state marginal that looks like this big red circle, I might say, well, maybe that view is not quite worth it, because in expectation, there are, even though there are some very good points in this circle, there are also some really, really, really bad points. So if you average together some big numbers and some extremely, extremely low negative numbers, maybe the average is very negative. But if my uncertainty looks more like this, maybe I'm pretty happy with the expected outcome. So it's not that I'm being pessimistic or optimistic with respect to my uncertainty. I'm simply taking the expected value, but the expected value already keeps me away from really, really risky things that have a non-trivial chance of an extremely adverse outcome. So the expected reward in our high variance predictions might be very low here, even though the mean is exactly the same. The mean is just centered at the goal. So I would choose not to do this if I have very high uncertainty. I would choose to maybe stay further away from the cliff out here where the circle wouldn't put me over the edge. And then, of course, when I do that, add that data to my data set and retrain my model, my confidence will increase, which means that the circle will get smaller. So maybe on the next iteration, I'll actually get closer to the edge of the cliff, and I will get closer and closer as I become more confident until I eventually get the good view without risking going over the edge in the process. So essentially, the intuition behind the problem, behind this problem and the solution of using uncertainty is that you're going to cause step 3 to only take actions for which we'll get high reward in expectation, rather than simply having a high reward for the mean. And this expectation is going to be with respect to our uncertainty about the dynamics. So this, to some degree, avoids exploiting the model, because now if our model is high variance, maybe it's predicting crazy values, so long as it has a good estimate of its uncertainty, it'll also predict that for those crazy values, it has crazy high variance. And then, of course, if we repeat the process, if we aggregate more data, goes to step 5, back to step 2, our model will get better in those regions and our confidence will gradually increase. Okay, there are a couple of important caveats with this, though, just to kind of clarify potential misconceptions. So this is, again, our picture, our cliffside, and we have our circle and our big circle. There is a little catch, which we have to be very careful about when we do this. If we want our model to get better, we do need to be able to explore. So simply saying, don't go to any regions with high uncertainty is not what we're suggesting here. Because if you simply avoid all regions with high uncertainty, then what you'll do is you'll avoid going to new places. We're not suggesting to do that. The idea here that I'm trying to get across is that if you take the expected reward, then you will avoid new places where there's a high chance of catastrophe. You'll still go to new places if you think that all the outcomes there are good or all the outcomes are neutral. You don't have to do that. You could also say, well, let's take the expected value with a pessimistic estimator. So instead of taking the expected reward, you can take maybe the bottom 10th percentile. That's sometimes referred to as risk-averse or risk-sensitive control. That is not what uncertainty-aware model-based RL methods do in general, but there is a separate class of methods, risk-sensitive or risk-averse methods, that use pessimistic estimates, usually for the purpose of maintaining some guarantee about safety. You could also do the opposite. You could take expected value with an upper percentile to say, well, take an action if you think it has even a chance of having a good outcome, and that can lead to better exploration. That can lead you to explore more aggressively, but it can also cause you to fall off the cliff a bunch of times. But in general, the expected value is often a good start, and just by taking the expected value with good uncertainty estimates, you can already get a lot of benefit without necessarily having to worry about being pessimistic or optimistic. That said, the pessimistic and optimistic stuff has a lot of interesting applications, and the optimistic stuff especially we'll talk about a lot more later in the class when we talk about exploration. Okay, does the basic idea of incorporating uncertainty about model-based RL make sense to anybody, to everyone, and do you have any questions? Okay, so now let's continue and let's talk about how we can actually get these uncertainty estimates. Because so far I just kind of assumed that your model tells you where it's uncertain. So can we get models that tell us where they're uncertain? And can we get those models to actually be large parametric models like deep neural networks? So here's one idea. Let's get our model to output a distribution over the next state. And let's use the entropy of that distribution to figure out if our model is uncertain. Most models you use already output some estimate of their distribution. So if you have, let's say, a model that takes in the state in action and predicts P of st plus 1 given st at, well, you have to represent this thing somehow. If your state is discrete, maybe you have a big softmax over all possible next states. So if you have a big softmax over all possible next states, that's of course defining a categorical distribution, and you can directly calculate the entropy of that categorical distribution. If you have a continuous state, perhaps you choose some class of distributions for P of st plus 1 given st at. Maybe you would choose a Gaussian, so your neural network outputs the mean and variance of a Gaussian, and that Gaussian also has an entropy. You basically just look at how wide the Gaussian is, look at the log of the determinant of its covariance. So both of these things will give you some idea of how uncertain your model is. So I'm going to claim that this is not actually good enough. Does anybody have any thoughts about why relying on the entropy of the distribution predicted by your model might not give you good uncertainty measures? It's kind of a tricky question. Yes, back there.
Because neural nets are like overly or not calibrated.
So the answer is, well, is it because neural nets are not calibrated? That is part of it. So there's actually kind of a two-part answer here. That's like the two parts are you're in a lot of trouble and then you're in a whole lot of trouble. So the you're in a lot of trouble part is that even for the data that the distribution of the model is trained on, these probabilities in practice often don't end up being very well calibrated, especially for extremely deep networks. Not well calibrated means that even though the network makes the right prediction, the most likely output is the right one, the probability assigned to those outputs might not actually be very accurate. That is part of the problem, but there's actually an even deeper problem. Even if we can fix the calibration issue, we still have a problem. Is there another answer? Yes?
Something about overfitting.
Something about overfitting, yeah. So that is actually what this picture is showing, something about overfitting. So let's go back to this picture, the picture that we used to motivate this discussion. So I said that, well, maybe imagine that this is a picture of how your model, your dynamics model fits the data, where the horizontal axis is a 1D projection of a trajectory, and the vertical axis is the reward assigned to that trajectory. Now, look at the blue curve. The blue curve represents the predictions from your model. The black dots represent your data. And here, it's continuous data, so maybe you use a Gaussian distribution, which means you're using mean squared error as your fitting criteria. The mean squared error between the blue curve and those black dots is tiny, which means that the optimal variance estimate will also be tiny. The model will tell you, I'm predicting Gaussian distributions over these points, and those Gaussian distributions have variance that's almost zero, meaning the model is very, very confident. It's a reasonable thing for the model to do because, given all this data, this is actually a perfectly reasonable estimate of the variance at those data points. It's just not a reasonable estimate of that variance in between those data points where the model wasn't trained. So what's the variance on this peak? Well, on this peak it should be very high, but of course the model wasn't trained on the peak, it was trained on the data points. So what this comes down to is that there are essentially two types of uncertainty. And when you're looking at the output entropy for a neural net, you're not looking at the right kind of uncertainty. Even if the network was calibrated, it's just simply not the right kind of uncertainty. What neural networks estimate when you train them to output either categorical distributions or Gaussians or any other kind of distribution on the output is aleatoric or statistical uncertainty. This refers to the uncertainty that's inherent in the data. So if I give you a data set like these black dots, there is noise in the data, meaning that there's some true underlying system, some kind of curve, and the data points are the consequence of taking points on that curve and corrupting them with some noise. And the variance that the neural network will assign, let's say if you fit a Gaussian distribution to this, is basically the amount of noise that it thinks there is that's being added to these black points. So this is uncertainty that's inherent in the data. The data is generated by some process, that process is noisy, and the neural network is estimating that noise. But there's a second kind of uncertainty, which is sometimes referred to as epistemic or model uncertainty, which is your uncertainty about the model itself. You can have a deterministic, noiseless process generating data, but still have uncertainty about the model that actually fits that data. You can imagine a really extreme case of this. If I have the same kind of regression problem, but I have one data point right here. Now, this model and this model and this model, they're all just as likely. And they all fit the data perfectly. But I don't know which one is the right one. So model uncertainty or epistemic uncertainty, it's simply a different kind of uncertainty. It's not uncertainty about the data point given the input. It's uncertainty about the model itself. So the neural network is going to estimate uncertainty about the output conditioned on the input. It's not going to directly try to estimate the uncertainty about the weights, about the model. So put another way, epistemic uncertainty refers to the situation where the model is certain about the data, but we're not certain about the model. So this model over here is very certain about the data, we just don't believe it. So discriminatively trained neural networks that are trained in the conventional way with maximum likelihood, are simply not attempting to estimate this uncertainty. They have no mechanism to do so. Which means that it's not actually enough to simply use the output entropy if you want to get uncertainty estimates that are good for model-based RL. So this should be estimate model uncertainty. There's a typo on this slide. So idea 2 is to estimate model uncertainty explicitly. So the problem is that the model is certain about the data, but we are not certain about the model. How can we estimate model uncertainty? So, well, for that we have to introduce a little bit of notation and a little bit more formalism. Let's say that our model has parameters theta, so those are the weights in the neural network. Usually, when we train a neural network with maximum likelihood estimation, what we're estimating is the argmax of the log likelihood. So technically what we should be doing is the argmax of the log probability of the parameters given the data. That's sort of the idealistic machine learning view, but of course if we use Bayes' rule, there's some proportionality constants that factor out, so in reality we can just do argmax of the log probability of the data given the parameters, which is what we usually do in practice. So data given parameters means P of y given x comma theta. But we know that by Bayes' rule, maximizing this is the same as maximizing the probability of theta given the data. If we want to estimate model uncertainty, then what we actually need to do is not take the argmax of P of theta given D, but actually estimate the whole P of theta given D. Because if we can actually estimate P of theta given D, then we can make predictions that take into account the model uncertainty. The entropy of P of theta given D tells us what the model uncertainty is. And if we have a particular input, st comma at, then we can predict the output by marginalizing out the parameters. And now this will give us a variance on st plus 1 that accounts for the model uncertainty and the statistical uncertainty. The statistical uncertainty just comes from the first term, and the model uncertainty comes from integrating out P of theta given D. So that is essentially what the Gaussian process was doing. In fact, the whole point of a Gaussian process is that it allows us to analytically integrate out parameters. Of course, we can't do that with neural nets, so with neural nets we need a little bit more machinery. But this picture, the reason that you're getting this green thingy and it has some distribution to it is because the Gaussian process accounts for both the model uncertainty and the statistical uncertainty. Okay, so of course, the key now is that we need to somehow get this P of theta given D, we need to be able to represent it in a tractable way, and then we need to be able to make predictions with it. So there are a couple of ways of doing this, some of which range from incredibly complicated to relatively simple. One popular class of extensions to neural network models that allow us to explicitly model P of theta given D is what's referred to as Bayesian neural networks. So in regular neural networks, every connection has a weight on it. So the weight matrix is basically just a matrix that consists of the connections between the neurons, and they're just numbers. In a Bayesian neural network, every weight is instead a distribution. And usually we pick some tractable class of distributions like Gaussians. So a very common approximation is to say that your distribution over the parameters given the data is given by a product of independent distributions. So you say that there's some uncertainty about every weight, but there are no covariances between the weights. Why no covariance between the weights? Well, because in a large neural network model, the number of weights is going to be humongous, and the number of possible covariances is the square of that. So that's probably a little too much for us to represent. But as a crude approximation, we'll just say, let's put a little bit of uncertainty on every single weight independently of all other weights, which gives us a product of independent distributions. And then we approximate the distribution over any single parameter theta I given the data with some tractable class of distributions like a Gaussian. So we might say, well, for every parameter we have a mean and a variance. So the mean is essentially the expected value of that weight, and the variance is how uncertain we are about that weight. It's a pretty crude approximation. We're losing a lot of information about covariances in there, but it's quite tractable. So usually when you see someone talking about Bayesian neural networks, usually but not always, they're talking about an approximation to P of theta given D as a product of independent Gaussian marginals. I'm not actually going to talk in this lecture about how to train Bayesian neural networks. I'm actually going to talk about a different, much simpler method for uncertainty estimation. But if you want to learn about Bayesian neural network models, I would highly recommend checking out these two papers, Weight Uncertainty in Neural Networks by Blundell et al. And Concrete Dropout by Gall et al. And these two papers describe two different methods for actually training these kind of weight distributions based on variational inference. We'll actually learn more about variational inference later on in the course, but if you want to get some ideas about Bayesian neural networks, check out these papers. We're actually going to talk about a different way of doing uncertainty estimation for neural nets that is very simple and tends to work quite well in practice, especially for model-based reinforcement learning. It's based on something called bootstrap ensembles. The idea is actually very intuitive. In the kind of old way of doing model-based RL that we discussed on Wednesday, we would take a neural network that accepts as input the state and the action and predicts as output a distribution over the next state. And that distribution might just be a softmax, or it might be the mean and variance of a Gaussian, something like that. All we're going to do now is we're going to train multiple networks. We're going to train an ensemble of networks. And then if we want to get an estimate for model uncertainty, we'll just see to which degree do these networks agree or disagree. So formally, we're going to approximate P of theta given D as a mixture of Dirac deltas. So we'll say each of these networks is a little spike in probability space, and the probability of seeing some parameter vector is 1 over n if that parameter vector corresponds to one of these models, and 0 otherwise. So that means, if you want to represent this visually, that you have some complicated distribution over your parameters, and you're just approximating it with a bunch of spikes, saying, okay, these spikes are going to approximate my distribution. It's a bit of a crude approximation, but it can work pretty well in practice. And then if you want to actually estimate this integral, the marginalization of the parameters, what you do is just average together the predictions of the different models. So here, what we really want is to integrate out P theta given D, but if P theta given D is given by this mixture, then all we have to do is average the predictions together under the mixture, which just means ask every model in the ensemble to make a prediction and average together the probabilities. Then the question that we have to ask, of course, is how do we train this ensemble so that this way of doing it actually works? Question.
Are they different models, or like the training process is different?
Yeah, so that's what I'm going to cover next. How do we train them? Yeah. So what we want, concretely, we want every model to be a sample from theta given D. So we have to train them in such a way that this actually holds. So the main idea in training this ensemble is to basically somehow make the models independent of each other. So the intuition is that you have one data set that you start with, and your models will be independent if they're trained on independent data. And it turns out that actually there's a way to kind of spawn off independent versions of that data set using the very same data that will result in independent models. So the way to do this is to train each model in your ensemble with parameters theta I on a different data set di. And if you could just obtain n separate data sets, you'd actually be done. So if you can just ask somebody to sample n completely independent data sets for you, that'll be good enough, and then you could train n independent models and do this. Of course, in reality, it's quite costly to ask for n copies of your, n separate data sets. So it turns out that there's a little statistical trick you can do, which is construct each of these data sets DI by sampling with replacement from your original data set. So sampling with replacement means that you're essentially putting an integer weight on every data point. So if I have my original data set, maybe my original data set has 4 data points. It has x0, x1, x2, and x3. When I sample with replacement, I'm going to populate a new data set of the same size by randomly picking a value between 0 and 3 for every slot here. So maybe here I'm going to pick x1, here I'm going to pick x1 again, here I'm going to pick x2, here I'm going to pick x0. That amounts to putting an integer weight on the original data set. So the weight would be 0, 2, or 1, 2, 1, 0. Right? So if you do this process n times, you get n separate data sets. And you can actually show that if you do this and train your theta i's in this way, you will actually get an approximation to the parameter posterior. Question?
The models are exactly the same, right? The parameters, like.
Right, exactly. So the models are structured in the same way. They're just trained independently of each other on these data sets that have been resampled from D. So this is a very old trick in statistics. It's not by any means specific to deep learning. So for any class of models, you can do this and you will get an estimate of uncertainty. It's not a particularly exciting or novel trick. It's just something that is simple and tends to work well. Question?
Is the output of that ensemble in practice, does it tend to just pick one of the submodels at a time? Like, I'm in that domain, that's the good model?
Yeah.
Or is it really doing a function of 3 models with like a
right.
function composition device?
Yeah, thank you for asking that question. So there's an important clarification that I think I should make here. Some of you might be familiar with things like boosting, for example, where the idea is that you would like to, or like add a boost or something, where the idea is that you'd like to have different models in an ensemble essentially take responsibility for different parts of the world. So you train the first model, you train a second model, so it corrects the mistakes of the first model, and so on. That is not what's happening here. The whole point of training the ensemble here is for all the models to be as independent of each other as possible, meaning that every model is trying to model the entire space, and they're trying to model it in different ways. The principle behind this is that if you have a small amount of data, every one of those models will overfit, but they'll all overfit differently. So if I have my data, maybe this is my data, and my model overfits and does this. If I train a second model and it's in some sense independent of the first, maybe it'll also overfit, but it will overfit like this. So then these models will agree near the data points, but they will disagree far from the data points. And that's what we want to see. If we're getting overfitting, we want to see the models disagreeing far from the data points and essentially overfitting in different ways. Yes?
So the big difference from bagging here is that we want to know the uncertainty.
That's right, yeah. So our goal is not to get a better estimate. Our goal is to get an estimate of the uncertainty. Sorry, but it's not to get a better estimate of the mean, it's to get an uncertainty. Now, there's actually a little more to this story if we're specifically in the domain of deep learning. So this is the slide about the principled, statistically sound approach of doing this. And as with all deep learning topics, there's the principled approach, and then there's the actual approach. And the actual approach turns out to be actually a little simpler. So this idea basically works as I described it, and you can implement it, and it'll do mainly the right thing. In practice, you're going to use a small number of models because deep neural networks are expensive, so it becomes a very crude approximation in reality to the true model uncertainty because the number of models in the ensemble will probably be pretty small. If you're training big neural networks, probably you're going to have less than 10 models, which means that you have some estimate of uncertainty, but it's kind of, it's not necessarily great. But the good news is that the resampling with replacement stuff, the stuff that I made a big deal out of at the bottom of the slide, is not actually all that important for deep neural network models in practice because the random initialization and the stochastic gradient descent that you're going to be using to train these models already makes the models sufficiently independent of each other. This is not a very principled statement, this is an empirical statement, but if you go and actually implement bootstrap ensembles, you can do so at home, and compare to what happens if you resample the data set with replacement versus just training all the models on the same data with different random seeds, you'll find that just simply training them on the same data with different random seeds often works just as well. So if you see somebody talking in a paper about training ensembles without mentioning anything about resampling with replacement, well, it's because they're aware of this fact and they just did the easy thing. All right, so that's the bootstrap ensembles in practice in deep learning. So now that we're armed with a technique for estimating uncertainty for our dynamics models, let's actually go back and use them for model-based reinforcement learning. So we've trained up our ensemble. We have these theta 1, theta 2, theta 3, et cetera, to theta n. And now we'd like to use them to choose actions. So before, if we trained up a deterministic model, F, then planning basically amounted to choosing the actions that maximize the total reward, where st plus 1 is given by f of st at. And then we just optimize over the a's. That's what you can do, for example, using random shooting method. Now, we can train an ensemble of models of the same type. For simplicity, let's first just talk about deterministic models that just make one prediction that predict st plus 1 from st at. You can still represent the model uncertainty by training multiple models in an ensemble, and then if you want to estimate the total reward of a sequence of actions, just average the rewards over the entire ensemble. And that effectively integrates out the parameters under this crude approximation that a small number of Dirac deltas approximate the whole complicated distribution. So this is a distribution over deterministic models. Now you can also use stochastic models. So you can have an ensemble of models, each of which actually predicts a distribution, and then you can have a more complex procedure for evaluating the reward of an action sequence. You would, in step 1, for every action sequence, sample a model from your posterior, which just amounts to randomly choosing one of the models in the ensemble. Step 2, for every time step, sample the next state from the distribution given by that model. Calculate the reward of the whole trajectory, and then repeat steps 1 through 3 until you've averaged together enough samples that you're happy with your estimate of the reward. Now, it's pretty easy to see why this thing is differentiable, which means that you can optimize it with gradient-based optimizers. You can also optimize it with stochastic optimizers. Basically, everything that we discussed last week, you can do for this kind of setting. It's a little bit less obvious to see why this kind of procedure is differentiable, but for certain classes of models, especially if you're predicting continuous states using Gaussian distributions, there's something called the reparameterization trick that you can do to differentiate through this. We won't cover the reparameterization trick today, but we'll cover it later on when we talk about variational inference. So you can definitely do this procedure if you're planning over actions with stochastic optimization, like random shooting or cross-entropy method. You can even use gradient-based optimizers for this kind of stuff, but it requires a little bit more work. Okay, so at this point, we've actually arrived at a procedure that we could use to implement a practical model-based RL algorithm that incorporates uncertainty via bootstrap ensembles. For example, a simple way to do this is to basically use this equation, train a bunch of models that predict the next state in your ensemble just by initializing it with different random weights, and you can get uncertainty and be a little bit robust to this exploitation issue. If you want to get really fancy, you can train complicated models that give you complicated distributions and use a procedure more like this. Any questions about this? Okay. There is a more complex option that you could use. So this is, for those of you that want to attach a name to things, this is kind of similar to Thompson sampling. You don't have to use Thompson sampling. You could also use what's called moment matching, which is exactly what that Gaussian process paper from the beginning was doing. So moment matching is going to try to maintain a parametric estimate of the state marginals. So the more general form of moment matching that's not specific to GPs is the following. Given a current estimate of P of ST, use your predictive model to estimate P of ST plus 1. And what you would actually probably get is some P bar of ST plus 1, some complicated distribution that is not in your convenient distribution class. Maybe it's not Gaussian or it's not whatever you want. And you can do this in a number of different ways. You could even just generate samples from P of ST, then generate samples from the corresponding P prime given S comma A, and you have a sample-wise estimate of P bar. But then you project this non-Gaussian p bar of st plus 1 to a Gaussian p of st plus 1, or some other nice convenient distribution. It doesn't have to be a Gaussian, but whatever nice parametric class you want. And the projection is just done with moment matching. And then you write down the expected reward under the state marginals of all the time steps and differentiate. So this is a different way to use uncertainty. This one actually tries to explicitly maintain a distribution over every single time step, whereas the one on the previous slide relies entirely on sampling. And both of them can work in different cases. Question?
So at the end of this, you still want to get a better estimate of the mean. You don't really care about like accurate measurement of the variance. Is that correct?
Right, so the question is, well, isn't all you care about an accurate measurement of the mean? Where's the variance coming in here? Note that this expectation is taken with respect to P of st. So if you have a very uncertain model, think back to the cliff example. If you have a very uncertain model, P of st will be very broad. So you'll be averaged together your reward over a larger region. So if you have some good regions and some bad regions, and your marginal is so big that it covers both of them, then you might actually have a lower reward once you average everything in expectation than you do at the center of that circle. So the actual variance doesn't actually appear in your objective directly, but it's playing a role indirectly because it's affecting this P of st. So you're averaging together a wider range of rewards. Okay. So let me give a little example of this. This is from a paper that used bootstrap ensembles for model-based reinforcement learning. So before we saw this picture, where with the model-based RL we were getting to a reward of about 500 on the cheetah task after about 10 minutes of real time. If you actually use an uncertainty-aware model, in this case just the simple bootstrap ensemble that I described, then you get to a reward above 6,000, so that will be over here on this plot, after the same amount of time. So if I were to merge this over here, you'd see this line going like this. So it makes actually a really big difference in practice to incorporate uncertainty into model-based RL. If you want to find out more about this topic, a few suggested readings on uncertainty in model-based RL. So this is the Gaussian process paper that I mentioned in the beginning. It's called PILCO by Mark Desenroth. And then there are some more recent papers that you can check out on deep RL that make use of uncertainty or bootstrap ensembles in some way. So I'll just throw up the list there, and then the slides will be online. You can check those out if you want to learn more. So if you're interested in exploring uncertainty, for example, for your final project, these things would be good to check out to see if you can get some ideas. All right. At this point, we're going to take a 3-minute break and come back at 10:59 and then talk about image-based models for model-based RL.
So the reason why it works with like a small number of models is because the accurate measurement of variance is not the most important thing. It's
Right, yeah.
We want to explore
Yes.
the space.
So think about the cliff example, right? So let's say that this is the cliff, and I want to go here, right? If I have one model that sort of predicts I'll end up here, one model that predicts I'll end up here, and one model that predicts I'll end up here, so here I get like a +1, and here I get like minus 1,000, and here I get minus 1,000 again. So even though I'm not really, maybe my full distribution is like this, I'm not representing it very accurately, but I get to see these really terrible samples.
Okay, so just like a random forest, like any other ensemble method.
Yeah, and of course it depends on the task. Like in reinforcement learning, there are a lot of tasks that are basically characterized by having a small region where really good stuff happens in the middle of a big plateau of really bad stuff. So if you want a robot to walk, there's a very narrow region of good walking and lots of really terrible falling. If you want a car to drive, there's a narrow region where it's on the road and lots of parts of state space where it's hitting stuff. So if your problem is characterized by those properties, then as soon as you start taking the samples, you'll see that there's the potential for the bad stuff to happen. All right, let's continue. So in the second half of today's class, I'm going to talk about model-based RL with high-dimensional observations like images. So we saw before when we talked about model-free RL that we could use algorithms like policy gradient and Q-learning to train policies that can do things like play video games from images. So can we use model-based methods with complicated observations like images also? So to recap, the version 1.0, we're going to work with the 1.0 version of the algorithm, but the same story holds for 1.5 and 2. The version 1.0 of the model-based RL algorithm consists of collecting some data, training your dynamics model to predict the future, using it to choose actions, and then executing that planner to get more data so that you can retrain your model. What we're going to need in order to bring this formalism to the world of images and high-dimensional observations is to bring back the partially observed Markov decision process model, the PUMDP model that we had at the beginning of the class. So if you remember, in the PUMDP model, we say that, well, your policy is going to act on some observations, and those observations are produced by the state, but they're not actually equal to the state. And in particular, the state is Markovian, but the observations might not be. So the key idea that a lot of model-based RL methods that use image observations are built on is that we're going to learn some kind of embedding of our observations, some embedding function that maps from observations to a latent representation of the state, and then use that latent representation of the state to actually choose actions. So instead of having policies that directly map from observations to actions, we're going to have some embedding function, G, that attempts to invert this generative edge from X to O, and then once we apply G to O, we get some kind of state that we can then use to choose actions. And we can use that state to choose actions either by learning a policy or by planning directly in the learned state space. So this basic idea has been actually explored in a number of different works. This part of the lecture is a bit more kind of research focused, so I'm mainly going to give examples of research papers that have done things like this because there isn't a single clear answer. But insofar as there's a theme to this, the theme is different ways of training this embedding function G and different ways of then using it to obtain actions. So the first example I'm going to give is actually a model-free RL example, but it's going to be a nice kind of introduction to the model-based stuff I'll talk about later. So this is actually from a slightly older paper called Autonomous Reinforcement Learning on Raw Visual Input Data in a Real-World Application. And the idea in this paper is to learn an embedding of high-dimensional observations, G of O, and then just run model-free RL in the learned space. And the particular task they're going to be trying to address is this little toy slot car. So there's a camera that watches this little toy slot car, and the camera images are used as the basis for making decisions about whether to accelerate or slow down the slot car to get it to go around the track as fast as possible without falling off the track. So the general scheme for the algorithm, which is going to be similar to the ones that we'll see for other algorithms today, is to collect data with some exploration policy. That's basically the step one in version 1.0. Learn some kind of embedding of your image observations, and then somehow use those embeddings for control, in this case, by running actually Q-learning inside of this embedding space. So how do we learn the embedding? Well, that's actually where there are a lot of different options. The particular option that's explored in this paper is to train what's called an autoencoder. So an autoencoder is a neural network that maps from an input, in this case the image, back to the same thing, back to the input. So it starts at an observation O and tries to map it back to itself. That seems like a very silly exercise. If you have an input and you want to train a network that just produces that same thing as output, one would think that a very good way to do that is to simply learn the identity function. The identity function is actually very easy to represent. So in practice, if you want to use an autoencoder to learn a meaningful representation, you need to regularize the autoencoder in some way to get it to actually learn a representation that is simpler or more parsimonious in some way than what you would get from just learning the identity function. And actually regularizing autoencoders to learn good representations is a very active area of research, and there's been quite a lot of progress since the time that this paper was written. So the particular technique they use is actually very simple, but there are much better techniques that exist today. The technique that they use is they say, well, we want our representation of the input to be low dimensional. That's actually one of the most basic things you could ask for. In reality, there are many other criteria that are more useful than being low dimensional, but that's a start. So what they do is they simply set up their autoencoder neural network so that it has a very small number of hidden units in the middle. And that layer, that bottleneck layer, is the one that they're actually going to use as their representation. So the loss for training the autoencoder is simply to minimize a square difference between the input and the output, kind of one of the simplest things you could think of. But because it has to be bottlenecked through a layer with a small number of hidden units, it's going to actually, in that bottleneck layer, learn a low-dimensional representation. So it's a lot like dimensionality reduction, only it's nonlinear because the autoencoder is a deep neural network and can represent nonlinear mappings from the input to the embedding. And then the first part of the autoencoder, the part that actually goes from the observation to the bottleneck layer, that's going to be our embedding function G. And the decoder we're just going to throw out after we're done training it. So in particular, what they learn is an autoencoder for the slot car task that has just 2 hidden units, which means that it's a 2-dimensional embedding of their observations. And then once they have this 2-dimensional embedding of the observations, their feature space, 2-dimensional spaces are pretty easy to handle, so they use a standard Q-learning algorithm with function approximation to learn their policy in that embedding space. So the embedding is a low-dimensional summary of the image. So what are some advantages of this kind of approach? Well, you can learn skills from images fairly efficiently because you just need to collect a bunch of random data, train this autoencoder, and then you have a very low-dimensional space to deal with. But the particular choice of embedding function is, it's quite delicate and it's a little heuristic, right? You don't really necessarily know that the autoencoder will recover the right representation. It'll pick out something that allows you to reconstruct the image, but not necessarily something that facilitates doing decision-making or control. So one of the ways that you can improve on approaches like this is to come up with models that are regularized to learn representations that are more like the kinds of representations that you might want. For example, if you believe that for doing model-based RL, it helps to have representations of the world in terms of, let's say, Cartesian coordinates of objects, you can choose a design for your neural network that facilitates the recovery of representations that look like coordinates of objects. So that's actually what's done in this paper, which kind of iterates on the same general formula, but now with model-based RL and a different choice of autoencoder. So the high-level structure looks very similar to the previous paper. You collect some data with some exploration policy. Then you're going to learn some embedding. Then we're actually going to use a model-based RL method here. So the particular model-based RL method is actually the one from the lecture on Wednesday at the end with local models. So with local models, if you remember, the idea is to run your latest policy, fit local linearizations around those trajectories, retrain the policy with the trust region, and then repeat. So that's the particular method that's used here. Of course, you could use some other one. But the main thing I want to talk about for this work is step 2, is the difference in which, the way in which this embedding is actually different from the previous one. So the idea here was to actually design a different autoencoder architecture, one whose bottleneck layer facilitates the recovery of object positions. And the design of this bottleneck layer is actually very simple. You have a convolutional encoder, and at the end of this convolutional encoder, what you do is you take all of the points in the convolutional response map, and you perform a softmax over the spatial dimensions, which means you exponentiate all of the activations and then normalize. So this gives you a probability distribution over spatial coordinates for every channel in the convolutional layer. And then you simply take the expected position under each of those. So if your conv layer detects, learns to pick up on different objects, maybe channel 1 picks up on one object over here, channel 2 picks up on a different object over here. When you perform the spatial softmax, that normalizes this whole quantity, and when you take its expected position, you basically get the centroid. And then you just pull out the coordinates of these things. So that gives you x1, y1, this gives you x2, y2, and so on. So you get a collection of features, one for every channel in your conv layer, that corresponds to a coordinate in image space. And you can actually visualize these coordinates. So here, there's a visualization of 2 feature points for a trajectory where this robot uses a spatula to scoop a little object into a bowl, and one of the feature points tracks the finger, and another feature point tracks the object. So this is just one possible design for an autoencoder architecture that perhaps has an inductive bias that's a little bit more suited for model-based control, because once you get these 2D coordinates, you can use them to do control. There are many other designs you can come up with for autoencoders that encode the kind of inductive biases that we might believe are important for model-based RL. There is another challenge that comes up when you start doing this sort of thing, which is that once you're embedding the observations to obtain a state representation, you start running into trouble when it comes to the reward function, because the reward function is conventionally a function of your state. But if you're learning your state, then you can't have a reward function that was pre-specified in advance because you didn't know what the state was in advance. So you'll often see in model-based RL papers that use images, there's a little bit of additional work that's needed to figure out what the reward signal should actually be. There are a number of choices, all of them suboptimal in different ways, but one fairly popular choice is to actually specify the task not by providing a reward function, but by providing a goal observation. So if you basically show the algorithm, this is what I want the world to look like, you can embed that state and then use the distance to the embedding of the goal image as your reward function. So then you'll say, okay, if I'm over here and I want to be over here, figure out how to basically make this image look like this image in the embedding space. So this is a video of this process in action. This is the autonomous exploration phase. This is what you're using to collect data to train your representation. So here the robot is playing with this object kind of with random actions until it gets enough data to train the embedding. And then now at this point it's actually already doing the model-based RL, so now it's trying to learn to get this object to the right location. And then you can also visualize the representation, which should come up shortly. So that's the final execution, and then hopefully it'll show the feature points. Oh, maybe it won't here. Okay, but the feature points are the ones shown here. So there's some points on the block and some points on the arm, and it's trying to get them to this location. Okay, now so far we've talked about embeddings that are trained in order to reconstruct a particular observation. So you take an image, you embed it, and then you decode that image. However, if we know that we're going to be using model-based RL downstream, we can actually construct our embedding in a way that is aware of the fact that you're going to be learning dynamics on it. So instead of actually regularizing your embedding to have the properties that you want, you can simply regularize it to be good for prediction. It's a very straightforward idea. It turns out to be somewhat challenging to realize in practice, but it can work well if you do it right. So the idea in this paper was to, again, similar recipe, collect data, learn your embedding, but now the embedding is actually learned jointly with the dynamics. So you learn the predictive model and the embedding together. And then in this paper, they actually used iterative LQR in the latent space learned by the embedding to do control. So that means that instead of just training G to embed the observations in X, you would train G together with P of xt plus 1 given xt ut. So this means that you're basically asking the model to learn an embedding that is easy to model for a predictive model. In this particular work, the way that this was done was by using a variant of something called a variational autoencoder, which we'll actually cover later on in the course, but I won't cover it in detail today. So here is a video of this method. So what they're showing here is for a simple 2D navigation task. This is the real state space, so it's just a 2D task. You're supposed to navigate from here to here while avoiding some obstacles. And what they're showing here is the embedding space as learning of the model progresses. So this model is trained to embed the observations and also model the dynamics in that embedded space. And here is the latent space for a different system. This is an inverted pendulum. And here things are a little more complicated because you have a pendulum with some angular velocity, and it comes up with this funny shape for the space. And then here's their illustration of the task. So on the left, it's showing the real image. It's a very simple image of just this inverted pendulum. And on the right is the prediction of the next step from the previous step. And then this is another task, cart pole balancing. So fairly simple tasks, but kind of decent predictions from training the embedding and the dynamics jointly. You can actually take methods of this type a step further, and you could actually say, well, let's try to learn an embedding of the observations that not only allows us to predict the next state, but also allows us to predict the next state in a way that makes it convenient for control. So one example of this is it's a very recent paper, uses the local linear models that we discussed on Wednesday to perform control. And then if you know that you're going to be linearizing your model in order to do control, what you can actually do is you can train the embedding in such a way that linearization gives you good predictions. So the way it's done in this work is by imposing a prior on the dynamics between successive states. So you can say that, well, okay, when you go from state x0 to x1, that transition is modeled by some dynamics, and we'll actually put a linear prior on those dynamics, saying that we believe that linear dynamics are more likely than really complicated nonlinear dynamics, which will then make that model easier to linearize. So that amounts to saying, find a way to embed these observations in a space where dynamics are easy to linearize. And that might be a good thing if you know that you're going to be then using that space to do control via linearization. So if you want to find out about the details of how that works, you can check out this paper. I'll show a little video just to illustrate kind of what happens there. So this is actually a video on a real robot learning to stack these little Lego blocks. And what it's doing is first, it collects a little bit of data that it uses to train up that embedding and together with the dynamics model in the embedding. And then it performs this model-based RL with local linear models, just like we discussed on Wednesday, but now with the state being the embedded state learned by the model. So this basic recipe of taking your observations, embedding them in some latent space, and then doing control in that latent space is actually one that's been explored quite a few times in model-based RL. It has a few challenges. The resulting models that you have to build are a bit more complicated than maybe the typical discriminatively trained neural net, but it can work well, especially in somewhat contained environments like this. That said, you can actually bypass the learning of the embedding space and try to do predictions directly in the space of observations, and then do control that way. So instead of learning some embedding G of O that gives you a state, you can just say, okay, forget about this, let's just predict future observations directly. And this can be a little simpler in some cases because the research into deep neural network models that can predict future images from past images, sometimes referred to as video prediction, is actually a very active area of research, and there are quite a few decent models that do a good job of predicting future video frames that can just be trained on videos from the internet. So you can adapt this approach if you want to find out about that for control. You can check out these two papers, but the basic idea is that you train a model, some kind of big neural network model that takes in an image and outputs the next image conditioned on the action. So if you can train a model that takes in an image, predicts the next image conditioned on the action, then you can unroll that model for many steps in time. In these particular works, the model was a little more complicated. It's based on a convolutional LSTM type setup, meaning that the model itself actually has memory about the past, which is important if you have partial observations because then you want to be able to keep track of things that might be in the world that are not seen from the current image. But there are many different ways to set up models like this, and even simple feed-forward models can actually work in simple domains. The recurrent models tend to work substantially better, though, for this sort of thing. And then once you train a model like this, you can look at the predictions that the model makes, and you can ask it to basically predict different future images conditioned on different actions. So what you're seeing here are some predictions from a convolutional LSTM model, this model over here, that was trained on data of a robot pushing objects on a table. And for each row here, all the images in the top row start in the same place. So they start with the same real photograph, and all the images in the second row start from the same real photograph. But every column is provided with different actions. So this is basically asking the model, predict for me what will happen if I apply different actions starting from the same place. And of course, if you can make these predictions accurately, then you can use this for model-based RL. You can take your current observation, sample many different action sequences, ask for predictions for each one, and then pick the one you like. Or do something more complicated like cross-entropy method to actually plan over actions. The big challenge that starts to come up when you decide to go this route instead of actually learning the embedding is that specifying tasks becomes even harder. So before we said, well, you could embed a goal image, try to match the state variables and so on. Here we get a little bit more of a challenge in terms of specifying the goal of the task because we don't even have a learned state representation. All we have is pictures. So we have to somehow specify our task in terms of pictures. There really isn't a great answer to how to do this. I can tell you about one approach that seems to kind of make sense in robotics, but this is actually something that I think people haven't really figured out how to do really well. So one approach that you can use in robotics is you can say, well, if your goal is to move objects around in the world, you can say, well, let's ask my model to figure out the action sequences that moves whatever is in this location to this location. So if your model is predicting future images, you can also ask it to predict motion between images. And then you can say, well, predict future frames and also tell me how this particular dot is going to move. The model doesn't know a priori about objects, but it does know about pixels. So you can say, well, predict the motion of this pixel. And the heat maps that you're showing in this bottom row, that you're seeing in this bottom row, are basically the predictions about the future location of that pixel. The predictions are a bit uncertain. That's why you see it spreading out as it goes further in the future. But something like this you can then use to select the action sequence that produces the motion closest to what the user commanded. So with that, you can do simple things like reach out and grab a stapler and push the stapler to a particular location. But of course, in the general case, you might want other tasks, tasks that are not easily defined in terms of locations, or even tasks that are not easily defined in terms of images. So coming up with better ways to specify goals for model-based RL with images is actually an active and open research area. The last thing I wanted to mention about model-based RL is that so far we talked about a very specific approach to model-based RL where you're predicting the future, specifically predicting everything about the future, predicting the entire future state or even the entire future image. There is quite a bit of work that looks at model-based RL in a slightly different way where you're predicting other quantities that are perhaps a little bit more narrowly scoped than the entire state space or the entire observation space. The choices here get a little bit more ad hoc, and it kind of depends on which problem you're trying to solve. But you could, for example, ask a model to predict, if I take a particular sequence of actions, will my robot successfully pick up an object? So what you're predicting is a small, low-dimensional quantity, like does it succeed at picking up the object or not? Or if I take a particular sequence of actions, will I collide with an obstacle or not? Or in the case of this paper, if I take a particular sequence of actions, and I'm playing this video game, what will be my health level after those actions? What will be my damage level? What will be my score? What will be my whatever? So that you write down a vector of quantities that you believe are relevant to the task and try to simply predict those quantities conditioned on a sequence of actions. This can be a bit easier if you know what those quantities are. So if you have some knowledge about the task and you can pick out those quantities, it's easier to predict those than to predict everything about the world. But of course, it requires a little bit more domain-specific engineering to select the right things to predict. So the benefit is that it's generally easier to train models like this. The downside is that you need to be able to pick those quantities and you need to be able to observe them in your data. You need to be able to automatically extract them from your data so that you can create your data set. Okay, does anyone have any questions about model-based RL from images or anything else that I covered in today's lecture? Yes?
So when you're talking about the encoder, you said that once you're done training sort of the encoder and the decoder,
Mm-hmm.
basically you can throw away the decoder network.
Yes.
Is there any way you can actually get some value out of the decoder network?
Yeah, so that's a good question. For those of you that didn't hear, the question was, well, you trained this autoencoder, and basically all the methods that I talked about today, except for the direct video prediction, is based on some kind of autoencoder. So the encoder is this, the decoder is this. So you train that thing, well, what do you do with the decoder afterwards? One thing you could use it for is to make nice videos. So if you remember this thing, the image on the right is actually formed by the decoder. The decoder has no role in actually doing control, but it can make some nice videos. If you want to, you can imagine this might be a useful thing for interpretability. For example, with the video prediction method that I showed before for the robot, for this thing, one neat thing you can do is you can say, okay, let's ask this model to do something for me, and it's screwed up. Why did it screw up? Let's look at the predictions. Oh, it's screwed up because it predicted that this object would actually move when in fact it wouldn't. So it can help you a little bit with interpretability. Any other questions? Okay, well, that's it for today's lecture, and I'll see you all next week.